BBH Colloquium. Very excited to have our speaker presenting today. And I wanted to notify the audience that the session is being videotaped, and the question and answer following the colloquium also will be taped. Now it is my pleasure to introduce Natasha Burse. She's a first-year BBH graduate student working in the lab of Dr. Lori Francis. She will be introducing our speaker today.
Good afternoon, everyone. It is my pleasure to introduce Dr. Anna Marsland. Dr. Marsland was born in Birmingham, England. She became a registered nurse in England and then received a Ph.D. in health psychology from the University of Pittsburgh. As a postdoc fellow, Dr. Marsland worked at the University of Pittsburgh Cancer Institute in the Behavioral Medicine Oncology Division. Currently, Dr. Marsland is a professor in the Department of Psychology and Nursing at the University of Pittsburgh. Dr. Marsland's research area is psychoneuroimmunology. She is interested in associations between acute and chronic psychological stressors, immune responses, inflammatory responses such as C-reactive protein and interleukin-6, and she's also interested in immune-related diseases such as childhood cancers. In addition to her education and training, Dr. Marsland was elected to serve on the Psychoneuroimmunology Research Society Board of Directors. And her other professional services include Associate Editor of the Journal of Psychosomatic Medicine. And of course, she has multiple publications in this journal. Her other contributions include mentoring and serving on numerous undergraduate and graduate student committees. And she has presented at over 100 professional conferences in the US and overseas. Please join me in welcome Dr. Anna Marsland.
Can you hear me? That's the microphone. Yes. Okay. Thank you very much. That was a lovely introduction. Very nice. And thank you all for inviting me here to give a colloquium and to talk about some of my research. I had lunch with some graduate students, and now I'm not sure that I'm going to talk about the thing that necessarily is the most interesting to everyone here, but I plan to talk today about a part of my research that focuses on inflammation and cognitive aging that happens during midlife. And I'm going to start off by talking just a little bit about why we've become really interested in midlife aging processes. And then tell you about the results of 4 sets of studies that we've done looking at inflammation, its relationship to cognitive functioning and changes in cognitive functioning across midlife, and to brain morphology and changes in the structure of the brain that begin in midlife and presage decline into dementia. And that's something that I've become, one of the areas that I've become interested in more recent years. Okay, so, let me just make sure I can find it. So, probably in this audience, these are not necessary slides, but just to set the tone, we know that there's a growing problem with cognitive aging, with high rates increasing rates of individuals living with dementia. Just to really point this out, if you look down here, this is the 1990s. I'm sure you can't see this, but this is the 1990s right here, going up to the dementia in 2050 right here, broken down by age, and you can see this unbelievable increase in the number of victims expected with dementia. And here, this just shows you this data in a different way. This is change in the number of deaths between 2000 and 2010, so this is actual change. And here we can see decreases in numbers of deaths as a consequence of cancer and heart disease that are fortunately happening at the same time as this increase, because people are living longer, and we've got this increase in rates of dementia. In fact, we have 5 million individuals living with Alzheimer's disease in the United States at the moment. It's the 6th leading cause of death. And 1 in 3 seniors dies with dementia. And in 2017, dementia will cost the US economy about $259 billion. So it's clearly something we need to be concerned about. And what we have here on this slide is just showing you the trajectory of cognitive decline over time. And here we have individuals that start off with normal brain functioning, and what we're looking at here is, as years go by, is the decrease in cognitive functioning. So here we have normal aging, and normal aging for most people is associated with some declines in cognitive functioning. Certainly on average, there are declines in cognitive functioning. But here we have people that show these preclinical declines in cognitive function that ultimately set them on a trajectory towards mild cognitive impairment, and then in later life on a trajectory towards dementia. I'm really interested in this period, this preclinical period here, where you can see it's already separation of those trajectories of cognitive decline, with some individuals showing accelerated decline in midlife years, which I'm going to show you in a few minutes, is really the area that we're talking about. So in none of the work that I presented today are we talking about individuals who are already showing cognitive impairments. Okay, so the cognitive functioning I'm going to talk about is declines that happen within the normal range. But what we know is that individuals who show more rapid declines in midlife are on a trajectory that dramatically increases their risk of mild cognitive impairment later and of dementia much later in life. Okay, so this tracks normal aging now. And when we look at normal aging, these graphs, I don't know how well you can see them, but I can point out, you can get the principle from them. This is from Tim Salthouse's review that was done in 2011, and basically just looks at chronological age along the bottom, and here we have a number of different cognitive functions. So if you can't see, you'll have to believe me that these top two look at kind of executive functions. This is processing speed, this is vocab, this is reasoning, this is spatial visualization. At the bottom here, we have tests of memory. And the point I want to make with this slide is that the age here, unfortunately for many of us, is around 30 years of age. And on average, from 30 years of age, what you're seeing here is gradual decrease in performance across a multitude of cognitive domains. This is normal aging. This is not anyone with any impairment. Most of these people are still functioning within the normal range at the beginning of this decline. But if you look at the rate of change, which is the lighter colored graph on each of these, you can see that that rate of change does not change much. The rate doesn't change. So if an individual is showing a steeper decline across midlife, they're likely to stay on that trajectory into later life and be at much increased risk for dementia. Just to ram the point home, I guess, here we have changes in memory function from age 25. Here these are individuals in their 30s, and we have a 15% reduction in memory function detectable on average in the 30s, and this increases until we're 65% reduction when people are in their 70s on average. I'm not talking about, there are some people who absolutely retain full cognitive function right the way through life and don't show these declines. So what I'm talking about here is average decreases that we see. Why do we care about these? Well, we care about these midlife declines in cognitive function because of what I've been saying. They predict these trajectories, because ultimately they impact people's quality of life. We know that individuals who show accelerated cognitive aging are at increased risk for physical injury, for hospitalization, and ultimately for accelerated rates of mortality, early mortality. We also know, and this is what we've been really focused on, is that it predicts risk for dementia. So, a lot of the work that's looked at dementia has focused on factors that relate to dementia and relate to the transition from mild cognitive impairment to dementia, or relate to the speed of the progression of dementia in later life. But what we've argued is that we really want to, if these trajectories are happening in midlife and are beginning when people are in their 30s and then characterize individuals across life, if we want to try and intervene and identify modifiable risk factors, we need to be looking much earlier in the lifespan than a lot of the research has been doing. Okay, so if we think about declines in cognitive function and what predicts declines in cognitive function, one of the things that is associated with and predicts declines in cognitive function is changes in brain structure. And here, in parallel with the early declines in cognitive function, from around the mid-30s onwards, you see a loss of total brain volume of about 0.2% per year, and this accelerates a little in later life to 0.5% per year above age 60. So this graph here actually shows you the decrease. This is again starting at, I have to look closely, at age 30. This is the decrease in total brain volume up to age 80. This is the rate of change over here. So it's a pretty stable rate of change from age 30 onwards. Okay? This graph down here actually shows the increase in the volume of the ventricles, the brain ventricles, over that same period of time. And what these graphs show you down the bottom here is that this rate of shrinkage of the brain is not uniform across the whole brain, and that the frontal lobes and the temporal lobes are particularly vulnerable. So there is greater loss of brain tissue in those regions of the brain. And these are regions of the brain that are associated with the most profound changes in cognitive functioning that you see with aging, which is kind of executive functioning, which we think of as something that is related to frontal lobe functioning, and of memory functioning, which of course we think of as being related to components of the temporal lobes. So when we look more closely at the brain, what you see here is this shows you over age, this is from age 22 to 82. This is the decrease in total gray matter volume. And what you see up here is the areas in blue are the areas where age is associated with a reduction of gray matter volume. So this is large areas of the cortex where you're actually seeing this reduction taking place. So what actually is interesting is that these changes in brain structure, in brain morphology, actually predict the changes in cognitive function. So, for example, age-related declines in total and white matter volume of the prefrontal cortex actually predict declines in executive function tasks that are served by these areas of the brain. And down here you can see age-related declines in hippocampal volume predict decreases in memory. So, not surprisingly, these seem to be related to one another. So we've become interested in midlife and what's happening in midlife and what's happening. This is part of a larger program that's happening at the University of Pittsburgh, which is looking at changes in midlife and how they predict risk for a range of different diseases. And my piece of this is looking at cognitive changes and changes in brain morphometry that presage these cognitive changes. Now, when we think about risk factors, it gets complicated. I know a lot of you probably are interested in different types of risk factors. And there are many risk factors that have been shown to be associated with midlife brain changes that we know relate to cognitive function. They include things like cardiometabolic factors, there's genetic vulnerabilities, cortisol dysregulation, blood pressure, high blood pressure, oxidative stress. But what I've been really focused on in my work is the role of inflammation. And I've considered the possibility that inflammation contributes both in concert with these other factors, but also potentially independently to risk for cognitive aging across midlife. Okay, this is like preaching to the choir, I think, with this audience. So let me just do a couple of minutes on inflammation and what we'll be looking at here. So I'm not going to spend too long on this. It's funny because I do teach immunology at Pitt to our students, so I could spend a long time on this, but I'm just going to talk about the fact that there's an innate immune response, which is an inflammatory process. You're very familiar with it because if you get splinter, then you have this red, inflamed, painful, swollen area around it, which represents the consequences of that inflammatory response. But I really want to point out the role of a number of cells, but the primary cell here being the macrophage, which is resident in tissue, becomes activated when it ingests a foreign particle or debris and starts to produce pro-inflammatory cytokines. These pro-inflammatory cytokines coordinate the local inflammatory response, but from our purposes, what we're interested in is the fact that they enter peripheral circulation. And then they have an impact on distal organs. They impact the liver and cause the production of the acute phase response, which of course we can detect as the levels of C-reactive protein in peripheral circulation. But they also have an impact on the central nervous system. And so we know, and this is well mapped in animal studies, that pro-inflammatory cytokines play a role in communicating about peripheral illness to the central nervous system. And actually they bring around a number of changes that we commonly think of as the sickness syndrome. So this includes things like general malaise, fever is caused predominantly by interleukin-6. So in an acute situation, this is what makes you feel yucky when you have a cold or the flu, and makes you feel like going to bed and cuddling up under the covers, okay? But what's interesting to think about is that as people age, their level of these systemic inflammatory mediators increases. You know, there's lots of potential reasons for this, and we can talk about this later if it's interesting, but it certainly is thought partially to represent sort of cumulative levels of inflammation throughout the body that increase with aging. Okay? So here this is Janky Koch-Glazer's work showing increases in pro-inflammatory IL-6 with age. This has been replicated a number of times, and actually we see increases in our own work in a number of circulating markers of inflammation that associate positively with age. What happens with these circulating mediators is that they can access the central nervous system. This is a well-characterized pathway. This is just a cartoon that summarizes a lot of research that's shown this. But here we know that, for example, around circumventricular organs in the brain, the blood-brain barrier is thin, and there are actually areas where pro-inflammatory cytokines can diffuse across the blood-brain barrier to access the central nervous system. We know that in other regions there are active transport mechanisms that transport pro-inflammatory cytokines across the blood-brain barrier. And of course, we also know that there are vagal afferents that are stimulated by pro-inflammatory cytokines in the periphery and actually communicate that there's an inflammatory process going on to the central nervous system. Within the central nervous system, pro-inflammatory cytokines stimulate microglial cells and astrocytes, and they in turn produce pro-inflammatory cytokines themselves within the central nervous system. And in animal work, these levels of central pro-inflammatory cytokines parallel levels in the bloodstream. So we know, and it's a clearly mapped pathway, that peripheral inflammatory mediators access the central nervous system, result in central inflammatory processes from these predominantly animal work. We also know that they bring about these sickness symptoms, and in animal work you can block these symptoms by giving antagonists for these pro-inflammatory cytokines. So I'm not going to talk too much because I want to jump into the human data, but this line of inquiry rests on a pretty established animal literature. And so animal studies, there are now a large number of animal models, some of them are cited down here, that show that if you peripherally give pro-inflammatory cytokines, if you infect animals with an infectious agent, if you stimulate animals peripherally with endotoxins, you cause a peripheral inflammatory response, and that you can get detectable increases in pro-inflammatory cytokines in the central nervous system. And particularly, there are receptors for pro-inflammatory cytokines throughout the central nervous system, but they are particularly concentrated in the prefrontal lobes. They're also highly concentrated in the hippocampus. And Animal work is focused on the hippocampus because models of learning in animals focus on long-term potentiation and the role of the hippocampus. So what you see is that these increases in central inflammatory cytokines interfere with long-term potentiation, interfere with neurogenesis, synaptic plasticity. They actually, if they're over extended periods of time, result in dendritic atrophy, and they impair hippocampal-dependent learning and memory in the animal models. This effect can be blocked if you give, for example, IL-6 antagonists. Based on this animal literature, the early work I'll show you in a second of ours really focused on the hippocampus. But since then, we've kind of broadened this, as I'll show you. But really, the animal literature has focused on the impact of inflammation on hippocampal dependent learning and memory. This is not news to you because you probably all know that when you're not feeling well, you're not at your best cognitively. And so this is results of an old study now, but I think it's straightforward and simple and makes the point, where this is a double-blind crossover study of 12 healthy males who were given E. coli endotoxin or saline, and the blue lines here show increases in peripheral levels of pro-inflammatory cytokines. This is TNF-alpha, this is IL-6, and about 2 hours after they were given the endotoxin, you see this increase in circulating levels of these pro-inflammatory cytokines. This would be expected, part of the inflammatory response to the endotoxin, but what's interesting here is that you see that as there are greater increases in IL-6 peripherally are associated with poorer performance on a word learning test. So, and as I said, you don't need me to show you this because you all know this. You all know that when you have a really nasty cold or the flu and you're not at your cognitive best, it's not a time for you to take in, learn new information, recall that information in the future. So it's not difficult for us to understand that this sort of acute immune response is associated with, in an acute situation, with declines in cognitive function. There's also, in the elderly, a large literature that shows that higher levels of inflammatory cytokines like interleukin-6 associate with poorer cognitive functioning in the elderly. And not only do they associate with poorer cognitive function in longitudinal studies, they predict more rapid decline or more rapid acceleration of dementia. So this is pretty well established in the elderly, that high levels of inflammation, and actually among people who have cognitive impairment, acute illness actually can aggravate their dementia and can send them for periods of time into much poorer cognitive functioning while their levels of inflammatory cytokines are raised, and they regain that after the infection passes to some degree. So, at last, we get to my research, which really is examining these inflammatory markers, whether they associate with brain structure in midlife adults, and whether they associate with cognitive function that we're interested in as a marker of risk for future dementia. And these are studies that I've been doing in collaboration with a number of people, and my disclaimer is that I'm learning quickly, but I'm not a neuroimager by training. And I do a lot of this work in collaboration with Pete Generis at Pitt, who has done a lot of neuroimaging work, as you probably know. But we're basically employing structural neuroimaging to get measures of brain structure. And then we're asking to what extent does inflammation and other risk factors associate with these brain markers of aging here in a way that might make us identify factors that are associated with increased vulnerability. So I'm going to tell you about very briefly, about 4 studies that we've done that are sort of beginning to suggest vulnerability in midlife associated with inflammation. And the first study is going to look at the association of circulating markers of inflammation with hippocampal volume and with cognitive function. Now, let me just give you a prelude to all of this, is that all 4 of these studies are performed on healthy midlife adults. So they're between the ages of 30 and 55. We have 3 separate cohort groups that we look at, but their recruitment is very, very similar. They're all community volunteers from Allegheny County and the Pittsburgh area. And they're recruited and at baseline are in pretty good physical shape. So this is a healthy sample of midlife volunteers. Okay? All of these are. So the first one is based on the Adult Health and Behavior Project, which is Steve Mannett's first cohort that he brought in. There are actually over 1,000 in this cohort, but at the time of this study, we looked at about 500 individuals, where we were able to look at inflammation, hippocampal volume, and cognitive function. So first of all, the cognitive function. The participants of the 500 we looked at, the first 500 that were recruited, there's the age range. As I said, they're all about 50% male, they're all around 80% white, which represents Allegheny County. And this is the AHAB1 cohort, has the best neuropsychological battery. Obviously, this is the AHAB1 cohort was developed as particularly focused on the development of cardiovascular disease risk. And so this was kind of an add-on to that, but it's a reasonably comprehensive neuropsychological assessment that was done. The assessment was done on the same day that IL-6 was measured, which is a good thing. We have the full Wechsler memory scale for those of you who have interest in cognitive testing. And we also have a couple of tests of executive functioning, the trail-making test, and the Stroop interference test. So this was our first foray into this. This is now a long time ago that we did this. But basically, we provided some of the first evidence that during midlife, we see the same pattern as you see in the elderly, which is that higher levels of circulating IL-6 were associated with poorer performance on a range of different memory tasks and on executive function testing. Okay. And this is that same data, it's just shown a little differently here. Here you can see this is individuals are split into tertiles on the basis of their level of IL-6. The blue bars are low IL-6, going to the yellow bars, which is the highest tertile of IL-6 right here. And you can see here, this is Wechsler memory subtests, 4 of them, that the pattern is that the higher the IL-6, the poorer performance. Now it bears repeating here that their performance is all in the normal range. There's no one who is showing impairment on these tests, which we wouldn't expect to see. This is a 30 to 55-year-old sample. These are healthy, functioning midlife adults. So they're showing normal cognitive function, but we're seeing this association with inflammation. Down here, you see a similar association for executive function testing. It goes in the opposite direction just because of how these different scales are scored. But you can see that basically what this shows us, higher scores on the Stroop, lower scores on Trails B are associated with poorer cognitive function. So the same pattern is seen here. These associations are independent of age within the sample, sex, race, body mass, education, blood pressure, smoking, and physical activity. And so they're pretty robust to a number of different covariates. A number of these are also risk factors for cognitive aging. And on a subgroup of this sample, we had neuroimaging. This was an add-on supplement to the initial AHAB trial. So we did not have neuroimaging on all of AHAB1. But here, for 76 individuals, we did have imaging that allowed us to determine gray matter volume of the hippocampus. And this was done by voxel-based morphometry from MP-RAGE images that we obtained. And here is a region of interest analysis. Now, we focused in early work on the hippocampus. We focused on the hippocampus with an a priori model based off the animal literature. So we were really thinking at the beginning that this was a focused effect of the hippocampus, and the hippocampus played this specific role, which it does play a role in learning and memory. So what did we see here? We saw that this is levels of IL-6. As levels of IL-6 increase, the volume of the hippocampus decreases. And you can see these associations right here. This shows you the left hippocampus. We picked these images to really demonstrate the left. But right here you can see slightly less, but still significant. We saw this in both left and right on the hippocampus. We saw this after we controlled for age, sex, race, and total gray matter volume. And we also saw a significant association on the left after we controlled for body mass. I'm going to come back to body mass at the end because it's something I'm intrigued by and we need to think more about. The association on the right-hand side fell to just below significance, so the effect size decreased a little when we put body mass in there. Okay, so that was our sort of first step into this, and we were intrigued by what we found. So I went on and looked at other cohorts where we had imaging to see what else we could take a look at. And the second study is based on a different group of subjects, but I was intrigued by this because for this group of subjects we had imaging that was done called diffusion tensor imaging, which permitted us to look at white matter integrity. Okay, so this is Ph.D. cohort. This is a cohort of just under 200 who have come in and very, very similar, recruited in the same way as the AHAB cohort, demographics virtually overlapping, healthy midlife sample here, but who have come in for much more intensive imaging. And that includes this, as I said, this diffusion tensor imaging that we did, which really offers an opportunity to look at the integrity of white matter tracks within the brain. So very briefly, diffusion tensor imaging permits you to look at the movement of water molecules within tracts within the brain. So if you have an intact tract within the brain, water molecules should be moving along the length of the axon. Okay, that's the way they should be going. That suggests an intact neuron that's myelinated and the water is going in that direction. What happens with aging or with damage is you start to get water molecules moving in a perpendicular direction. This means they're going out of the axons, which indicates that the myelination is actually has broken down to some degree. It's not a healthy tract, and the more that molecules are going in this direction, the less healthy that white matter tract is. This is used as a marker of white matter integrity in the brain. The measure is actually called fractional anisotrophy, and here just shows you in this situation, this is low tract integrity. This is the movement of the water molecules. You can see they're kind of going in all different directions, which is mapped right here, and this is a low level of integrity, and high integrity right here, you can see they're moving along the direction of the axons. By doing these measures, you can actually create a map of the white matter tracts within the brain. And what is shown in this figure right here is from another study which shows you associations of age with the integrity of those white matter tracts within the white matter skeleton. And the areas in blue are the areas where you see a decrease in white matter integrity with age. And so what happens here, and this happens unfortunately starting around the late 20s, is you start to see decreases in the integrity of these white matter tracts within the brain. And you can see here, this is actually what's called perpendicular diffusivity, which is the radial diffusivity is the molecules moving in the wrong direction, and you can see that increases with age. So we had this kind of imaging on the PIP project, Ph.D. project, and we were able to derive this map of the white matter tracts within the brain. This is the mean of the subjects that were in the study, 155 subjects. We then could ask, to what extent did our measures of inflammation correlate with white matter integrity within the brain? Here, in this study, we had actual measures of IL-6 and C-reactive protein. And what you can see here is that higher levels of inflammation in midlife are associated with lower levels of tract integrity. We also had MP-RAGE scans, so we could look at grey matter volume and white matter volume, and what we saw that higher levels of inflammation were associated with lower levels of total grey matter volume and lower levels of white matter volume. All of these associations remain significant after we controlled for sex, age, and body mass. We didn't, unfortunately, in the PIP project, have a neuropsychological testing battery. We did have a measure, an unusual administration of the Stroop task that was given in the scanner, part of a functional imaging protocol, and we were able to show that levels of IL-6 and CRP correlated with poor performance on the task, the Stroop task that was done in the scanner, so replicating some of our earlier findings. And this just shows you the maps. The areas in red here are areas of the white matter skeleton where you see an inverse association of CRP in this figure with integrity. Now, what's interesting here for us as we were thinking about this is we did have some predictions. We kind of predicted that we would see specific tracts affected. Those tracts that we've been focused on, tracts that involve the temporal lobe and particularly the frontal lobe, those areas of the brain that show greater shrinkage with age and may be associated with early age-related changes in cognitive function. We did not see that. We didn't see specific tracts affected. This was widespread and scattered throughout the whole brain, was the association of inflammation with white matter structure. Okay, so the third study that we went on to do was in the second AHAB cohort. This is a completely new cohort of individuals recruited in exactly the same way, but who this time came in to participate in an imaging protocol. So this gives us many more scans to look at. And so we had imaging on 415 healthy volunteers from this study. Demographics the same as the other cohorts. We have inflammatory markers, IL-6 and CRP. These inflammatory markers were, as expected, reasonably highly correlated with one another, so we created an inflammatory index by combining them. I will tell you this though, all of the results I'm presenting hold up if you look at either of the inflammatory markers alone, and I'm just going to show you the combined results. We had a shorter cognitive battery than in AHAB1, but a cognitive battery that included memory testing and some other tests here. And what that enabled us to do is to create domains of cognitive function. We had a verbal proficiency domain, we had short-term memory, spatial reasoning, executive function, and verbal memory. And what we saw is we replicated our early findings with our combined inflammatory marker being associated with poorer performance across these cognitive domains. And here you can just see this for, this is spatial reasoning right here. This just shows you the scatter plot. This is for memory, this is the scatter plot, and this one is for verbal proficiency. And so we then went on to start to think about the structure of the brain and what we were seeing. Here we did not have diffusion tensor imaging in this study, but we were able to use free surfer to parcel the brain into distinct areas and then take a look at the association of inflammation with those specific areas. What we saw was a replication of what we found before, was that inflammation was associated with decreased total grey matter volume, decreased total white matter volume. Interestingly, using free surfer, we were able to actually take a look at surface area, and so individuals with higher levels of inflammation had decreased cortical surface area. And also we saw, when we looked at specific regions, a decrease in total hippocampal volume and decreases in a number of different prefrontal regions. We also, this is just confirming what we should see, which is in this study, age was inversely associated with all of these measures of brain structure here. And also actually with an increase in inflammation. Okay, So here we have these structural measures. Here's inflammation associated with cortical gray matter volume. This is inflammation associated with total gray matter volume, and here with cortical surface area. We went on because we had the power in this study to statistically look at mediation, to ask whether the associations that we saw between inflammation and cognitive function were statistically mediated by measures, and we started off looking at total gray matter volume up here, and what we saw was that there was evidence for mediation, and so for partial mediation, I should say. What you should notice here is that C prime, this direct pathway, remains significant even when you have the indirect pathway in the model. So it's certainly not explaining the whole effect at all. But we have total gray matter is one of the factors that possibly could contribute to the association of inflammation with verbal memory. We also saw this exact same pattern of results when we looked at the other cognitive domains that we looked at here. Findings were independent of sex, age, total intracranial volume, smoking, blood pressure, and race. Okay, and I already said that the direct paths for all of them remain significant, so it's certainly not the full explanation by any means. We've been really playing with this idea of to what extent is this a global effect versus a localized effect. And so what's intriguing here is that we did see a specific impact of gray matter volume of the temporal lobe. So in models where we looked at the gray matter volume of the temporal lobe, we adjusted for, controlled for, the other three lobes, the volumes here, we saw an association of inflammation with spatial reasoning and short-term memory that was independent of the gray matter volumes of the other lobes. Did I say that right? That makes sense. So it was an independent effect of the temporal lobe here, which suggests that there may be a global effect, but there may also be a specific impact on certain brain regions, and in our results, the temporal lobe appeared to be one of those areas. We just went backwards. Voxel-based morphometry is not as great a way of looking at this as the free surfer parcellation that we used later was, but we went back and we just tried to replicate our original findings. So we used voxel-based morphometry to look at the hippocampus, and we replicated an inverse association of our inflammatory measure with hippocampal volume, which you can see here. And these areas here of the prefrontal cortex were areas where we saw an inverse association of our inflammatory marker with the prefrontal cortex right here. And interestingly enough, when you look at a number of these, particularly the memory function, we saw the same pattern of results here with partial mediation of the association of inflammation with verbal memory by the hippocampal volume. And this is partial mediation of inflammation with short-term memory by areas of the prefrontal cortex. So, I wanted to come back to body mass, because I'm intrigued by body mass. I'm also intrigued by cardiometabolic risk in general, and whether inflammation contributes to these associations independently of these factors. So this gets complicated with these risk factors because they overlap, and that you find them, they hang together within individuals and create these cumulative metabolic risk parameters. So is inflammation useful? Does it contribute to anything over and above these is kind of the question that we were interested in. You may or may not know that body mass index, first of all, associates with inflammation pretty strongly. Part of that's because adipocytes are one of the primary cells that produces pro-inflammatory cytokines. Indeed, people have suggested that up to 40% of circulating levels is coming from fat cells. So, no surprise here that our inflammatory score associated highly with body mass index, okay? And probably that's where these inflammatory markers were originating. We also, this is not novel at all, there is quite a considerable literature showing that body mass associates inversely with a number of the different markers of brain aging, including here total gray matter volume, and also that body mass associates inversely with the cognitive functions we're looking at. So our question became, is it just body mass? Do we need to take blood from these people? Can we just stand them on scales? Well, I've already kind of implied as we've gone through that most of the associations that we saw were independent of body mass. So if it does account for it, it doesn't account for all of it, and there's an independent effect of inflammation over and above body mass. But what is intriguing is that what we showed is that associations of body mass with gray matter volume and associations of body mass with cognitive function were partially mediated by inflammation. So it kind of raises this possibility that inflammation is a common pathway that might be associating body mass with these kind of neurocognitive measures that are associated with risk for dementia. We saw the same pattern, I'm not showing you the data here, with metabolic syndrome. So inflammation contributed to these changes independently of metabolic, over and above metabolic syndrome, but also it accounted for and partially mediated the association of metabolic syndrome with brain morphology and with cognitive functioning. So we are in our current work really interested in sort of these patterns of risk and the possibility that inflammation is a sort of final common pathway that may link these other risk markers to cognitive decline. So I'm going to finish here, I think, with these conclusions and leave us enough time for questions. There is another study, but it kind of takes us in a different direction. But let's just do this. So among our midlife adults, higher circulating levels of inflammatory markers in these three separate cohorts we've replicated, that they're associated with poorer cognitive function, that they're associated with decreased global and regional gray matter volume, with decreased white matter volume and white matter integrity. And that there's cross-sectional evidence that possibly brain morphology may mediate the association of inflammation with cognitive function. So we think this is preliminary support for a neurobiological pathway by which inflammation could impact brain systems that are important for cognitive function and might be an early marker of a number of early markers of vulnerability for cognitive decline. All right, let me skip through this because I just want to show you next directions. There we go. So, obviously some limitations of the work I've showed you. It's cross-sectional at this point. I'm happy to stand here now and tell you we have at last been funded to follow up both AHAB1 and AHAB2 cohorts. So we have AHAB1 participants will be starting to come back within a month, actually, and we will be following up on them 15 years after the original assessment, which will be really nice, looking at a lot of changes over time in that cohort, but I'm particularly interested in looking at changes in their neurocognitive function and trying to use our markers to predict those changes. And we've just got funded as well to bring the AHAB2 cohort back in and re-image them 10 years after their baseline imaging, which will be really nice for us to look at structural brain changes over that period of time and to try in a better way to tease apart risk and predicting change over time, which I think is the next step for this program of research. And so I think that's pretty much what I had. I just want to say a huge thank you to the crew in Pittsburgh, which I learned today is only 2.5 hours away, and it's a fun city to come visit. But Pete and Eris, without whom I would not be doing any neuroimaging work, that's for sure. Steve Manick, who has the 2 cohorts that I work with, Matt Muldoon, who's the MD on our project, Janine, who's been very involved in our neuropsych assessment, and these are staff members who have just been hugely instrumental in the work that I have presented today. And also, of course, NIH and NIA and NHLBI for funding this program of research. Thank you.
questions?
Whether or not one hits more strongly, or do you tend to, are you able to lump them together in some of your work as a general marker delineation? So in that last study, we lumped them together, but then we saw a similar magnitude of effects for both of them. I can't say that we see one. It's interesting though, because IL-6 can get into the central nervous system, and in healthy individuals with healthy brains, CRP cannot. And so we presume that CRP is functioning as a marker of some of the pro-inflammatory cytokines that can access the central nervous system. But we don't see any difference in the magnitude of the effect. Yes?
So based on animal models, one of the studies is going to measure the stress. Do you have any information on stress history of co-partners?
We do. I have not seen much of stress in playing with this, but I don't think we have great markers of stress. It's not like the animal literature where you can do these nice clean studies and expose to stress. So we have things like we have a life event measure where we ask people if they've had significant life events from a list of life events in the past 12 months. The hit rate in this age group was not particularly high for having had significant life events. We have measures of perception of stress, and we didn't see much with perception of stress, but it's very hard to sort of parallel those animal models for us in this kind of example. But no, the markers, the measures, the self-report measures that we have, we did not see.
Along those lines, is there any evidence that there's monocytes along the lineages of the brains of these people that apparently source cytokines for the brain, the monocytes that line in the lineages?
I would, just from what I know, I would imagine really we have not a way of measuring that in this stage at all. I would imagine that that's really obvious. Yeah.
Did you take a look in your subject in terms of how much anti-inflammatory is there safety on that?
We did, and actually, I didn't mention this, but yes, we do. And we control for it, it doesn't take away the effects or make a difference, interestingly enough. So, not a high rate of anti-inflammatory used regularly. My guess is when we bring them back 15 years later, we'll probably see more people regularly taking anti-inflammatories for pains, etc. But in this group, as they were functioning, we did not see that. This is a very healthy group. Anyone who had any sort of cardiovascular issues at baseline was not eligible to participate. So we kind of, it makes it even more remarkable. Frankly, it would be interesting to see what we would have if we had a true cross-section of people. But I think we'll be getting, 15 years after this, we're getting some of these people into their late 60s. We're going to see a lot more going on, I expect. But at this point, no.
Thank you for that. In the tensor imaging data, did you noted and were somewhat surprised by the fact that the damage was relatively local and not in a consistent location. Do you think those levels of patterns of damage could be consistent with vascular mechanisms, microstrokes, or other things that are damaging very small areas?
We don't in this age group in this healthier population, no. But we don't have evidence of that, but the base rate should be very low in this group, is my understanding, and this is coming from people who know way more about this than I do. This came up, was brought up in a review about one of the studies, and we provided a lot of data to really suggest that in this age group, the mean age of the sample was in the 40s. And so in this age group, you're really not looking at a high base rate of those things. So I don't think so. We don't have good measures of it, so it's very hard. What you saw is the association scattered throughout the white matter skeleton, which is kind of, I think, is intriguing. So, yes?
Another one. I noticed you had a lot of health behaviors and health risk behaviors, and I would be remiss if I didn't ask if you had addressed the role of sleep and either the relationship to your pro-inflammatory state, potential mediator, and independent of inflammation, or via.
I'm glad you asked that question. We do have measures of sleep, self-report measures of sleep. Yes, only self-report. We have actigraphy in another study, but only self-report in this study. Sleep quality associates with inflammation. Poor sleep quality associates with higher levels of inflammation. Sleep contributed very little to the associations that we saw with cognitive functioning or with the structure, brain structure. But it definitely appears to be associated, was associated with both inflammatory markers, and certainly in AHAB1 and PIR. I'm pretty sure that's the case. We usually see that. I'm pretty sure it's the case in AHAB2 as well. Yes.
So I was intrigued by something you had on a very early slide, which is when you're looking at the trajectory in this pre-symptomatic period. It seemed that there were a few statements as to whether the patient or the individual is aware of.
In that one slide there is. So actually this is really interesting, and I don't think we fully understand this yet, and this is, we certainly haven't, we actually don't even have measures in any of these cohorts of self-awareness of cognitive decline. We're including those measures in we've just been reviewing this literature, and we're including those in the follow-up study that's about to start. But what is interesting is from the literature, it appears that people are aware of these slips in their cognitive function way before they're detected by any of the neuropsych tests that are being done. And they are pretty reliable in predicting these trajectories. So there is an awareness, which, hey, I certainly know that I'm subject to not being as cognitively capable as I was 10 years ago. And I think there is an awareness of this.
Yeah, well, wonderful talk.
Thank you.
Dr.
Thank you
Marsland.
for inviting me.